Okay, so we've got this data here, this 8-bit data, and we want to put it in a SECDED code word, meaning that we want to be able to correct single errors and detect dual errors with our code word. So the first thing is we need to compute it, right? Our transmitter, before it sends it out, is going to take this data and figure out what the 5 check bits should be, right? We've got our single error correction check bits and then our dual error detection bit. So, as always, what I like to do is I like to make spots for all my bits. So I can have, let's do another color here, let's do, so we're going to have bit 12 and 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. And let's underline my check bits, right? So 1, 2, 4, and 8. And then 0, that's my dead bit. And my dead bit is very significant, so I'm going to underline it twice. You know, I'm even going to underline it 3 times, right? The reason I say this bit is significant is, well, because all the bits are special, but this one is extra special because the order that we compute it sort of matters in that the dead bit, or the dual error detection bit, covers all of these bits. And we know what the data bits are, right? I can just go ahead and write those in there right now, right? That's 0, 0, 0, 1, 0, 0, 1, 1. I can write those in right now. But the dead bit covers bits 12 through 1, right? It's the exclusive OR of all of them. And if I don't know what 8, 4, 2, and 1 is, I can't compute bit 0 yet. So that means I need to do 8, 4, 2, and 1 first. So let's do that. C1, that equals the exclusive OR of bit 3, which is a 1, bit 5, which is a 1, bit 7, which is a 0, bit 9, which is a 1, and bit 11, which is a 0. So what should this even parity bit be? It should be a 1. Now let's do C2. And C2, so that's going to be the parity bit of 3, which is a 1. 6 and 7, that's 2 zeros. And 10 and 11, those are 2 zeros. Oops, trying to see. So it looks like here our parity bit should be a 1, because we have 1, 1, which is an odd number. Now C4, and C4 is 5, 6, 7, and 12. So 5, 6, 7, and 12. So we've got 1, 0, 0, 0. And so that turns out to be a 1. And last but not least, let's do C8. XOR, and that's 9, 10, 11, and 12. So 1, 0, 0, 0. And once again, this parity bit comes out to be a 1. So, wait, did I do C4 right? That was 5, 6, 7, and 12. 5, 6, 7, and 12. Okay. So, I kind of pull these data numbers out of my butt when I do these examples. And so all the examples so far I've done, C1, 2, 4, and 8, have come out to be all 1s for the computation. And that is just a coincidence. That's what happens for those cases that I've picked. But they're not always going to be 1s, right? All it would take is this 3 to be flipped to a 0 to change this 1 and this one. So just pointing that out, that we do have to calculate these. They're not always 1. Anyway, let's plop these in here now. So we've got C1 is a 1. C2, let's make a distinguished color. Let's do this nice burgundy. So in this case, all of our check bits are 1. So I'm just going to put 1s in here for all of them. And now, the big daddy is C0. And that is the XOR of, I'm not going to write them all, I'm just going to say all the bits. Right, excluding 0, right? You can't, it's not going to parity itself. So let's look at all the bits here. We've got 1, 2, 3, 4, 5, 6, 7 ones. So 7 ones. Since there's 7 ones, that's an odd number. So we need to make it even by, there's another parity of 1. So that means here, let's make it pink. Screw it. We'll put a 1 there. And there we go. That is our entire SECDED code word. So we would ship out all 13 of these bits to our receiver, and our receiver would kind of have to do this, the whole process again, and see if there's any errors, 1 or 2 errors, and if there's 1, it can even correct it. If there's 2 errors, it would say, hey, can you repeat that? And so that's what we'll do in the next example.